Alright, today we're going to start 10.1 and 10.2, so we're going to be simplifying and verifying using fundamental trig identities. So we did see a little bit of this back in chapter 6. Also, I'd like to apologize ahead of time for the rain and thunder that you may hear in the background. It just adds to the mystique of math. Also, the thunder just adds to the fact that verifying fundamental trig identities is my favorite part of trig, and I can't contain myself, so the thunder represents that. Alright, so our first example is using trig identities to evaluate the remaining trig functions. This is not the best way to go about this type of problem. Drawing a triangle is a lot of times easier and quicker, but this works, and so that's why we're just showing it as an example of something you can do. So if I want to find the values of the other trig functions, well, right here I know I have cosine of pi halves minus theta equals 3/5. Therefore, that's my cofunction identity, so I know sine of theta equals 3/5. So it's using the identities. Now, if I know sine, then I know cosecant is 5/3. If I know cosine, I know secant is 5/4. Now we want to find tangent and cotangent, so we could either use the Pythagorean identities or the quotient identities. Either one is going to get you the correct answer. So for instance, I could say tangent of theta is sine of theta over cosine of theta, which is going to be 3/5 over 4/5 or 3/4. And then I know cotangent is, cotangent is the reciprocal of tangent, so then cotangent of theta is going to be 4/3. Just to show you as an example, to find tangent, we also could have used the Pythagorean identity, so I could have said tangent squared of theta equals, and I know it's secant squared of theta minus 1, and we said up here that secant was 5/4, so this is 5/4 squared minus 1, and then we can solve and take the square root, recognizing that we need it to be positive, so we'll end up with the 3/4 as well. Again, this type of problem, we're not going to spend a lot of time with this because it's not the most efficient way to do it necessarily, but it is a use of trig identities. Okay, so now on to the first step. So this is simplifying. This is going to lead into verifying. Simplifying, so we're trying to take these, what were originally given as an expression, and we're trying to simplify it. Now that's really generic, and so that's what makes this difficult, is we don't necessarily know when to stop. Sometimes it's obvious, sometimes it's not. So for example here, if I have tangent of x times cosecant of x, well, directly tangent doesn't relate to cosecant necessarily. If they were squared, they do through the Pythagorean identity, but as they are, they don't. So I can change tangent into sine of x over cosine of x, and I can change cosecant into 1 over sine of x. Now I can do a little bit of algebra, and I know that cancels, and I'm left with 1 over cosine of x, but 1 over cosine of x is secant of x. So therefore I've simplified it. So if I get it down to a single term with no mathematical algebraic operation, such as in here I had division. If I can get rid of the division, I can. So that's how I know that I'm done simplifying. This is not the only way necessarily to go about this problem, but this was one of the easier ways. So the trick is to figure out a relationship between the trig expressions that you're given and try to see how you can eliminate or reduce as many as possible. So I want you to pause the video, take a second, and try to simplify this trigonometric expression. Unpause when you're ready to check. Okay, so what I chose to do here is recognize that 1 minus cosine squared is sine squared from my Pythagorean identities. Cosecant is 1 over sine. So again, originally cosine and cosecant don't share some identity, and so I want to try to change one of them or both of them into something that is the same, or where they do share something. And they both can be changed in terms of sign. So then I have sine squared times 1 over sine, the squared and the sign on the bottom cancel, and I'm left with just sine of x. Again, pause the video, use your trig identities, try to simplify, unpause when you're ready to check. Okay, so first thing we want to do, anytime you see this pi halves minus x, get rid of that right away. So use your co-function identities. Don't use the sum and difference identities. It'll work, it's going to be a lot more work though. And then here I see cosine of pi halves minus x. Again, use your co-function identity right away, get rid of that. So this becomes cosine of x, cosine of pi halves minus x is sine of x, cosine over sine is cotangent. Again, we're done, I can't do anything more. You may start to think that all of a sudden all of these are going to simplify down to a single trig term. That is not going to necessarily be the case. So now I want to look at, well, what if I have tangent squared minus tangent squared times sine squared? So the directions are telling me factor first, so that's giving me the hint. If it didn't say that, then I need to recognize to factor first. So in this case, I can take out a tangent squared, and I'm left with 1 minus sine squared x. Well, what's 1 minus sine squared? 1 minus sine squared is cosine squared. What's tangent squared? Tangent squared is sine squared over cosine squared. Now these cancel, and I'm left with just sine squared of x. So I want you to take a minute, pause the video, and try to factor and simplify cotangent to the 4th x plus 2 cotangent squared x plus 1. Alright, so here we want to recognize that this expression originally is of quadratic form. So I can factor it like a quadratic, and it actually factors into, it would be a perfect square trinomial. Cotangent squared x plus 1 times cotangent squared x plus 1. Cotangent squared x plus 1 is cosecant squared. So I end up with cosecant squared times cosecant squared, which is cosecant to the 4th. Alright, a couple more. So here I want you to try and simplify sine 4th x minus cosine of the 4th x, and then secant squared x minus 1 over secant x minus 1. So again, pause the video, unpause when you're ready to check your work. Okay, so the first one here, I recognize this is the difference of squares, and I factored into sine squared x minus cosine squared x times sine squared x plus cosine squared x. Sine squared x plus cosine squared x is 1 from my Pythagorean identity, so this stays sine squared x minus cosine squared x. I can leave my answer like that if I want. So sine squared x minus cosine squared x is an acceptable answer for simplifying this problem. If I wanted to try to change it, I could change it using the Pythagorean identity. So cosine squared is 1 minus sine squared, so it would simplify to 2 sine squared x minus 1. Or I could change sine squared into 1 minus cosine squared, and I end up with 1 minus 2 cosine squared x. Or, although we have not done the double angle identities yet, so I don't expect you to do this at all, but I just want to show you that if you look on your sheet where the double angles are, or in the book, this would also become negative cosine of 2x. Again, I don't expect you to do this right now, but I'm just pointing it out. Okay, so if we look at the second one, this one's a little more straightforward, or there's less options, I should say. Secant squared x minus 1, I can factor that into secant x plus 1 times secant x minus 1 over secant x minus 1. The secant x minus 1's cancel, and I'm left with secant x plus 1. I cannot do anything else with this to simplify it anymore. You could change secant into 1 over cosine, but that makes it more complicated because it introduces division. So we can't do anything else. Also, we're really tempted to use a Pythagorean identity because we see a trig function and a plus 1, but it's not squared, so we cannot use the Pythagorean identities. Remember, those only work if they're squared. Other identities can work with other powers, but Pythagorean only works squared. Also, another hint here, so I didn't want to change secant squared x minus 1 using a Pythagorean identity up here because I already had secants. So remember, when we're trying to simplify, we want to try to be working with all the same trig function if possible. That will make simplification easier. So that's a strategy that you can use. Alright, last simplification one, so I want you to pause the video, simplify this, and unpause it when you're ready to check your work. Okay, so here's an example where I'm going to show you two possible ways to get the same result. One is going to be much longer and more rigorous, the other is going to be simpler and quicker. But both work, and that's the point, that you don't, as long as you get to the correct answer, it doesn't matter. So my first one, this is going to be the longer one, I wanted to get a common denominator, so I multiplied the top and the bottom of secant by 1 plus sine of x. I distributed the secant, so I ended up with secant of x plus secant of x times sine of x, and then minus cosine of x all over 1 plus sine of x. In the next step, now I wanted to change everything, so again, one strategy is try to get everything in terms of one trig function. If you can't do that, try to get it in terms of two. Well, sine and cosine are really nice. They work well together. So I can change all of the secants to cosines since I already have a cosine over here and I have some sines. So secant becomes 1 over cosine, secant of x times sine of x because sine of x over cosine of x. Don't change that into tangent. That'll eliminate what we just did. Remember, keep everything in terms of two trig functions if you have to. And then minus cosine of x, all over 1 plus sine of x. Now I multiply the top and the bottom by cosine of x to get rid of the fractions in the numerator. So cosine times 1 over cosine became 1, cosine times sine over cosine became sine, cosine times cosine became cosine squared, and in the denominator I have 1 plus sine of x times cosine of x. Notice that I did not multiply out the denominator. I want to keep that separate because I know that I'm going to try to reduce things, and I know that cosine times sine is not going to help me in any way. So now I changed cosine squared into 1 minus sine squared using my Pythagorean identity. If I distribute this negative, I notice that the 1's are going to cancel and the numerator is going to be left with sine plus sine squared of x. Still over 1 plus sine of x times cosine of x. Now in the numerator I can factor out a sine of x. So I have sine of x times 1 plus sine of x all over 1 plus sine of x times cosine of x. The 1 plus sine of x is cancel, and I'm left with sine of x over cosine of x, which is tangent of x. Bam, done. Now, that was kind of tedious. It was fun, but it was a little tedious. So, another method, and there are others as well, these are just the two that I'm showing you, is instead of getting a common denominator, multiply by the conjugate of 1 plus sine of x. The reason why I know that that's a good idea is that's going to create a Pythagorean identity that's going to help me with cosine. So in the numerator, do not multiply it out, but on the denominator I end up with 1 minus sine squared of x. 1 minus sine squared of x is cosine squared of x. Notice over here with the secant, I just casually changed that into 1 over cosine of x. So now the cosine in the numerator reduces with the cosine squared, so conveniently I created a common denominator, and now I have 1 minus 1, those cancel, plus sine of x. So sine of x over cosine of x is tangent of x. Again, much quicker, easier, neater. But either way works. If you did something else, as long as it was algebraically and trigonometrically correct, that's fine. You should get tangent x in the end though. Okay, last one for part 1. So this is a different type of problem, but we still use the identity. So perform the substitution to write the algebraic expression as a trigonometric expression in terms of theta. So do a substitution. So first, we're just going to substitute in for x. So the square root of 10 tan theta squared plus 100. Pause the video here and try to simplify it the rest of the way. Unpause it when you're ready to check your work. Okay, so after the initial substitution, now I can square both terms in here because this is multiplication, so it becomes 100 times tangent squared plus 100. Factor out of 100, so I have the square root of 100 times the quantity tangent squared theta plus 1. Tangent squared theta plus 1 is secant squared, so since this is multiplication, I can take the square root of both. The square root of 100 is 10, the square root of secant squared is secant. I'm done. Now you're going to go on to part 2 to do a couple verifying problems. Before we go on to that though, and this is included in the verifying, notice that with all of these you have to carry through the theta or the x or the theta or whatever is representing the angle. That variable has to be carried through, otherwise it's incorrect. So keep note of that. So now this will end and start part 2.